Okay. Hi, welcome to Strategic Design. I'm Austin Haddocks.
I'm Mike Corsetto.
And so I'm one of our lead strategy scouting, and I'm also a mechanical mentor on 1678. For my day job, I'm the head of data analysis and contract management for a local nonprofit. This is updated, my 13th season in FRC, and I've been with 1678 since 2019.
And my name is Mike Corsetto. I'm the head coach of Citrus. For my day job, I'm the director of hardware and systems engineering at an ag tech startup company. We build robots that pick fruit. I've been doing FRC for a little over 20 years now, and I started coaching 1678 in 2008 when I began my studies at UC Davis for a degree in mechanical engineering. A lot of the lessons that Austin and I are going to be talking about are a lot of trial and error and some stuff that's been gleaned from other great presenters over the course of many seasons in FIRST.
Okay, so just a quick overview. We're going to cover preseason prep, different drivetrain designs, mechanism designs, technical basics that are necessary for the season, build season, and competition season schedules.
Okay, golden rule number one. We're going to have 5 golden rules through this presentation. There will be a quiz at the end, so lock them down. You may want to write it down on your phone. Golden rule number 1 is keep it simple, silly. Anyone ever heard of KISS before? Yeah, the slogan? Silly is the moderate way to put it. The basic thing to remember here is building within your team's capability is probably the number one thing that you can do to improve your chances at competitive success in 2025. A lot of the other principles that we're going to talk about are actually based around keep it simple and based around building within your own team's capabilities. This is like the ultimate truth. It is very hard to know what your team's capabilities are, but the general rule of thumb is the simpler the thing is, the more robust it is, and the more robust it is, the more likely you're going to be successful at competition. Okay? Nope. And then what was the last slide? Oh yeah. And then the last bit here. This is a citrus specific portion of flavor, but I think it's worth mentioning is we prioritize function over form. Meaning, if you look at the average Citrus Circuits robot, it's pretty ugly. There's probably going to be better looking robots at the competition, but we prioritize the function over the appearance of the robot. And all of our resources go into the functionality, and we spend basically 0 time on how it's going to look.
So what's the purpose of the preseason? The preseason is not a break. It's the time to train your students, try out new designs, practice new topics, and learn and research past FRC games and designs. This is the time when you have the most free resources to try new things, and spending the time as a break is a missed opportunity.
Yeah, here's some ideas for off-season projects. This is like what Austin said. The training in the off-season is really important, and projects are a way to flesh a lot of different aspects of your team's workflow out at the same time. So it's not just exercise for the design team members, but a lot of these will encompass multiple areas of your team, from purchasing parts, bringing parts in, fabricating parts, obviously designing the parts, but then assembling them, wiring them up, programming them.
So it's so important to learn FRC history. FRC games are extremely repetitive in ways that you might not necessarily think about it. We just gave some examples. So in most of the last 10 years, there's been some form of climbing. There's been 2 examples of inflated tubes. 3 if you're going to include the inflated cubes in 2023. There were 2 examples of exercise balls. FRC is starting to love the concept of foam balls and foam game pieces. And so learning how those kind of compress and shoot is something that can carry on from year to year. And flat discs is another another concept that they're trying to stick with lately. And so the more that you learn about FRC games, what was the meta, how many game pieces were teams able to score, how did teams go about scoring the game piece, can be directly applicable to this year's game possibly.
Great, and that takes us into golden rule number 2, where we got 5. This is the second one to write down. Steal from the best, invent the rest. So I think the key principle here to think about is, and actually this comes with there's quite a few other seats if you guys are willing to spread out a little bit. There's some seats around here if you guys want to sit down so that other people can come in and pack and go for it. Find some open seats, there's plenty. Thank you. But the key principle here is that, like Austin said, a lot of the games are repetitive, which means a lot of the solutions that teams have come up with are similarly repetitive. And what that means is you don't have to, as an individual, as a designer, as a coder, you don't have to come up with all these unique ideas, all right? The thing that you should be starting with is the precedent, doing research, finding out what other teams have done to solve X, Y, and Z tasks, all right? And we'll talk about this a little later, but this cranks up to 11 once the season starts and once other people start releasing their ideas for the current game. But doing your research about past games is also really important. There's some teams to look at. Currently, teams like 581, 2056, 6329, these are great examples of teams that find really simple and elegant solutions to complex problems. So if you're wanting to look at these robots from the past couple years, I encourage you to. Some examples of stealing from the best and invest the rest that 1678 has directly benefited from include our 2013 robot, which didn't start out like it looks like in the upper right-hand corner. It started out as almost a totally different robot, and through the course of the season, we copied 254's intake and we copied 973's shooter to make some amalgamation of the two that became our first robot to get to Einstein at the championship level. And then fast forward 11 years, our 2024 robot, our beta robot, which we'll go over a little later, was terrible. And so we watched Spectrum's Open Alliance, which is what OA stands for here. And we almost directly copied their robot in a whole lot of ways for our competition 2024 architecture. So a lot of opportunities, a lot of resources available. The biggest thing to learn here with golden rule number 2 is you don't have to be smart enough to come up with a bunch of unique ideas to be successful in FRC. 1678 certainly does not come up with a lot of unique ideas to be successful. We are very good at copying other people's homework and making that successful. So
yeah. One thing I did want to say, a general rule though, don't copy 971. They build very complicated robots, and so though they're very good, not necessarily the best example to copy from. Golden rule number 3, use a proven drive base that's for you. So what we mean by that is if you have built an off-season robot or possibly in another season, with a drive base, you have experience with building, designing, programming that drive base, so then you can quickly assemble it during the first week of kickoff, and we'll talk about that in a little bit. But if not, the Kit Apart's drivetrain is specifically, they designed the game so that the Kit Apart's drivetrain can play the game. So, and if there's some changes to it, they sell adapters for the wheels at Andy Mark. So it's always a good solution for the game, and I know that Swerve is flashy, but if you haven't had practice putting it together and programming it during the off season, you're not going to be successful putting it together during the build season and building a functional robot at the same time. And so a special story.
Yeah, going back, 16 years now. Yeah. This is what 1678's robot looked like in 2008. The game that year had 2 components. There was a large, 40-inch exercise ball that you had to launch over this, almost like a high jump bar, over and over again. But then the field was broken up with a fence in the middle, so it kind of formed like a little racetrack, and you were only allowed to drive counterclockwise around the field. But there were only 2 of those big 40-inch exercise balls per alliance. And there are 3 robots per alliance. So one robot wasn't going to get to be one of the ones to launch the big exercise ball. So this was right before I joined the team. 1678 that year decided they wanted to be the third team on the Alliance and just race around the field. And they thought the fastest way to race around the field would be to build a race car and do this totally new style of driving for them, which was Ackerman steering, where the front wheels steer just like your car and the back wheel drives. Well, this is very different from most robots back then, which were tank drive robots. And they threw out the kit of parts tank drive that they got for free, and they instead built this crazy Ackerman steering robot. Well, this thing never really worked. The potentiometers that controlled the steering were always going out of function. There's some seats in the back right corner over there if you guys want seats back there. Thank you. And then the robot was actually designed so poorly that battery was like 12 inches off the ground. And every time it would do that quick turn around the racetrack, the thing would roll over. So it was only like this tall and it would flip over every match. So all that to say, this custom drivetrain that they built for the first time in season was not the move. And they would have been better off building just as simple of a robot, but with a tank drive that came in the kit of parts, and they would have been more successful. So, lessons learned there.
Yeah, so Swerve Drive, the most important part about Swerve Drive is don't figure it out for yourself. Use a COTS solution. There are many good solutions. Swerve is very complicated. There's a reason why for decades in first, there were 3 teams that successfully would use it. And the only reason that teams are able to successfully use it now are for companies like SDS, WCP, and Rev. We personally like SDS and WCP modules. They're easy to mount, and there's a lot of documentation on it. It is very programming intensive, especially for your first season working with it. And so it's really important to make sure that you have that time beforehand to test it. And it's a completely different way of driving. Our driver is right there, and I'm sure that he can attest that it would be very different than the standard tank driving. So it's really important that you give your driver enough time, especially if you're transitioning, to learn a completely new way of driving.
All right, so let's briefly touch on mechanism design, some of the key principles to keep in mind as you're going about designing everything above the drivetrain. Some of the examples of simple robots we were sharing earlier, minimum degrees of freedom. A degree of freedom is defined as any part of the robot that needs to move relative to the other part of the robot. Degrees of freedom can get more complicated as you add them to each other, okay? So a simple up and down elevator would be 1 degree of freedom, but it starts to get more complicated when you put a actuating wrist and maybe a clampy bit onto the end of that elevator, right? Now you're stacking degrees of freedom. And things, generally speaking, things get weaker, less robust, and more complicated the more degrees of freedom you have and the more degrees of freedom you stack on top of each other, okay? So thinking about minimizing that is an important part of effective robot design. And this goes to, we talked about keep it simple, we talked about that earlier, and an example of Lynx being a very simple robot. Every team, doesn't matter how experienced you are, can benefit from putting less degrees of freedom on their robot, all right? Try for less degrees of freedom and then add them back if you determine you need them. Low center of gravity, this is becoming more and more important. It used to be 10 years ago you could build a robot that was fairly unoptimized, was very tall, had some heavy stuff up top, and you'd be okay because the force that you were able to impart on the drivetrain was much lower. Robots are going twice as fast now as they did 6 years ago, okay? And especially in 2023, we saw a bunch of robots falling over because everyone was building robots like it was 1999 and it was 2023 and the robots were moving much faster. They're getting hit in the corner, spun, flip it over. So you have to put everything you can as low as possible because the robots, doesn't matter what type of drivetrain you have, if everyone's using brushless motors in their drivetrain now, they're gonna go fast, they're gonna hit even harder. You have to build low. Symmetry when possible, keeping things inside the frame perimeter if possible. We should have listened to that lesson this year because our over-the-bumper intake is very prone to breaking. It is not following a lot of these principles. It's additional degrees of freedom, which makes it more complicated, and it's outside the frame perimeter. Back to the point earlier, robots are going super fast now, and so anything that goes outside the frame perimeter is going to get abused harshly. So don't put stuff outside the frame perimeter unless you're absolutely sure that it can take a direct hit to the wall. And ours cannot take a direct hit to the wall, which is partly why we've had so many issues with it this year.
At least from an angle.
At least from an angle, and directly in sometimes too.
Yeah.
Great.
Okay, so with movement, there's 2 major ways to move something. There's motors. Now there's a wide range of different motors to choose from. Falcons, now Krakens, and there's a new, smaller Kraken coming out. You can have single speed or shifting gearboxes. Shifting gearboxes aren't really as necessary anymore.
We gotta delete that.
But with motors being so powerful, you can just kind of hook up some gears to it, and like one Kraken can kind of move the world now. They allow for variable movement, so if you need something to go from here to here and to here, it makes it a lot easier. They are harder to control. You're going to have to use sensors, and you're going to have to use PID loops. But with pneumatics...
Yeah, pneumatics are the other main mode of motion that you can implement in your robots. Pneumatics, if you're not familiar, they use compressed air from a compressor on board. And a solenoid, which is basically just a gate valve to choose which direction to plumb the air. And then you use that to move a cylinder rod in and out. And so you can do all sorts of things with this. The big advantages with pneumatics are they are very simple to use. They always go to one of 2 positions, which is often very convenient. It's not very software intensive either. And the pneumatics can also act as a dynamic spring, which might be helpful in some applications, because if you fully extend a pneumatic and then it takes a shock impact, it'll retract slightly and then bounce back. So that can all be helpful. Some of the downsides with it and why pneumatics are becoming less and less popular, they're very power inefficient. It requires an air compressor that's a simple brush DC motor, and it generates a lot of heat. Where'd that heat come from? It came from your battery. Now your battery's getting drained faster. And then it adds another level of complication as well. If you lose air pressure for whatever reason, all of your pneumatics on the robot are not working anymore. So there are upsides and downsides. It's still very much a viable component within FRC to use pneumatics for various functions. It can make for the simplest climb you've ever done. And actually one of the best teams in the world this year, 2056, had a very simple and reliable pneumatic climb on their robot this year. So it's definitely worth considering, but keep in mind what the pros and cons are of adding pneumatics into your robot.
Yeah, one last note on that is that keep in mind that there are a lot of motor slots now, but also teams are using all those motor slots, so maybe it's worth removing all the pneumatics and adding one motor instead, or vice versa, keep all your motors in place and adding pneumatics in place if you have to wait. So general rule of thumb, the larger the acquisition zone, or I guess, what is an acquisition zone? An acquisition zone is the effective area that you can touch a game piece and intake it from. So if I was to pick up a note this year and my intake was this big versus I could pick one up this big, I can be a lot less aligned and a lot less focused on the field and still pick up the note. It allows for easy driving. It allows for the robot to not necessarily be oriented in the right way, but it's really important that you stress the prototype really hard and that you iterate multiple times on the prototype to make sure that you have the right acquisition zone for your robot. There have been times where we've built a very large acquisition zone. Our rule is normally the entire front of the robot, but because intakes get hit, maybe it's worth having a slightly smaller one to fit into the right slot or whatever.
Great. That takes us to golden rule number 4, which is always use rolly grabbers. Okay, what I mean by rolly grabbers are, this year, probably a pretty obvious example would be most teams had an intake that composed of wheels close to the ground that you would then turn on, and then once the game piece hit the note, or once the game piece hit the roller, the note would go into the robot. We call this a continuous intake because it doesn't require any very specific timing from the driver and operator to make the function happen. The operator or the driver hits the intake button before you get to the note, and then the thing keeps going and going and going, and the second it makes contact, you've acquired it and you're on your way. This is the opposite of a non-continuous intake, which would be the example of like a claw or something else that requires specific timing to actuate and acquire the game piece. A great example of this is back in 2014. It was another year with really big exercise balls. Our robot that year had 2 rolling intakes on it that would spin, 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 and when it made contact with the ball, it would suck the ball up into the robot. Other teams had these big claws, kind of like the claws that you have in Toy Story, right, with all the aliens, and they're like the claw and it grabs them, right? It looked like that, but on the field. The problem with the big claw like that is when you're driving at this exercise ball at 20 feet per second, right, and you want to pick it up, and you have this claw open, the operator needs to decide when to close the claw. They run into the exercise ball, and then they're like, okay, I'm there, I'm going to actuate the claw, and by the time they get the claw actuated, the ball's already bounced off their robot and is 10 feet in front of them. So that's compared with a continuous intake where you just turn the wheels on 10 feet before you get to the ball, and the second you touch the exercise ball, it pulls into your robot. So that's the difference. Always look for times to run a rolling grabber, no matter what game piece it is. Try to approach it from the perspective of, can I turn on a spinning device of some sort and suck in this game element? That's what you want to be asking yourself.
So we have some robots here. Can anyone tell us, this is a little bit audience interaction.
Go to the next slide too.
Oh, okay, yeah, we'll do all of them. So what is similar about all these robots? And the answer is not that they're blue. Any ideas? Yeah. So there is one on here that doesn't. Does anyone know which one and what's special about it?
Okay, go forward 2 slides. Okay, so this robot in the bottom right is the only robot that doesn't have rolly grabbers. It had a pinchy claw to grab the tube, and this is the only 254 robot to ever not win a Silicon Valley Regional that it participated in. Every other 254 robot that you've seen has won the Silicon Valley Regional, except for that one, because they didn't have a rolly grabber. So that's the lesson. Want to go over this one?
Yeah.
All right, great. Electrical pneumatics, really quick. This is more of an example of what not to do. This was the inside of our 2013 robot, the one I talked about earlier, where we copied a bunch of other teams and went to Einstein for the first time. One of the reasons why we didn't win champs that year is because of exactly what you see on the screen. That was the wiring within the robot, and during semifinal match 3 on Einstein, there is somewhere in that mess of wire there's an air compressor, and somewhere else in that mess of wire there's a wireless radio, and the air compressor wasn't bolted down, and the wireless radio wasn't bolted down, and the air compressor slid into the wireless radio and unplugged the Ethernet cable, and so we were dead for half the match of our last match of that season. And so, if we had been following this advice that year, we probably would have made it a little bit further because we had paid more attention to the wiring inside the robot. And then the other thing that I tell the Citrus kids all the time is we're wiring robots, not statues. So what that means is this is a robot that will be in motion. It's going to be seen upwards of 10 or 15 Gs during certain impacts. And it has mechanisms within it that are moving around and moving past each other. So when you're going about wiring the robot, you need to keep in mind that this thing's going to be shaking like the dickens. It's going to be experiencing all sorts of loads. It's also going to be moving within itself, meaning that you can't wire something that has the chance of being rubbed on and or cut by another mechanism within the robot. So play around with how you're wiring things, make adjustments, use a lot of strain relief. Anything that's a big amount, when you're at 10 Gs, even a little bit of wire mass can multiply and then cause itself to fatigue over time and get failures within the robot. So you have to do proper strain relief, especially in this day and age where robots are moving faster than ever.
Yeah. So this is an outdated slide. But a general thing that all programmers are going to have to be aware of is that autonomous is kind of more important than ever now. They're designing games that can be won or lost in auto, especially early weeks of competition. And so it's really important to be using the built-in encoders on the motors and using that in conjunction with a gyro. Having some form of vision alignment. There's now the April tags on the field, so they're just giving you the locations, hoping that you use them to align. Using the Limelight is a great COT solution for this. There are now a lot more teams that are using their own solutions, including ourselves, but the Limelight works great. You are going to have to use PID loops for all your arms and elevators, making sure that it's going and being controlled to the right specific location, and using PID loops for spinning up your motors for your shooters and stuff is important too.
All right, let's talk about build season. Questions at the end. If you have questions, save them for the end. Thank you. All right, in the build season, when you're thinking about planning out what your season's gonna look like from kickoff through to your competitions, it's important that you set an accelerated schedule for yourself, okay? The saying here of like aim for the moon, land among the stars, the implication here is you need to set a very aggressive schedule because there's a high likelihood that you miss on your schedule, and you want your miss to still be within a reasonable time window, okay? If you plan your schedule out to line perfectly where like your last auto is being programmed the night before you go to competition, like that is not a recipe for success, because any slip in that schedule means that last auto that you need before competition never gets written, okay? So you need to set a really aggressive schedule. An example is actually, this is a picture I took of last year's schedule, and you can see that it has most of the mechanisms getting finished and running drive practice by the end of week 4, and we're going to go over that in a little bit. But this gives you an example of like most of these mechanisms, most of these stages of the process are only expected to take a couple of days at most, and a lot of things are being done in parallel too. Each of these are different major tasks that are on the schedule, and a lot of them are being run at the same time. So there's a lot that you need to plan out for. You need to plan out your process in a way that works for your team, but plan it to be aggressive because everybody assumes they have more time than they do, and you need to give yourself, your team, that sense of urgency early on in the season, rather than probably a very familiar experience for everybody is the night or the 2 nights before competition being very rushed to get the basics done before you go to competition. You don't want to put yourself in that spot, so plan aggressively.
Yeah, so kickoff, probably the most important day of anyone's season, is where you decide all of the aspects of your robot. What are you going to do? What are you going to focus on? And so we wanted to kind of highlight the fact that we're not building anything. We're focusing on just brainstorming the concepts what we're going to build and what are we going to do. And so on that brainstorming slide, you want me to?
Yeah, go for it.
Okay. So the 3 steps that we follow are, first, read the rules. Everyone reads the rules, and everyone has to take a rules test to show that they understand the rules. There's no point in discussing something that the robot should do if it's illegal. And so we make sure that everyone takes the test and passes before we start those discussions. We also post our rules quiz every year, so if you guys want to use that, it'll be on Chief. And then after that, we start with what are the ways to score, what are the things that are valuable for our robot to do, and we have a more detailed process in there where we list out what are the things that everyone thinks we have to do, what are the things that people think we shouldn't do, and then once those things that are easy discussions, then we talk about the harder things more in depth. And then the next day on Sunday, after we then finish talking about the last contentious points of the what's, we talk about the how's, which is how is our robot going to accomplish these? We said it's going to climb. How is it supposed to climb? What kind of designs are we looking at? And what should the shape of our robot be? That's what the how's of the second day is.
Yeah, great. Austin went into the what's a little bit, but I'll expand on it because there's a lot of really important stuff there. Some things that you can talk about during your what's discussion are what are all the various tasks the robot can accomplish, and what are those tasks worth? If they're worth points, what are those point values? And then trying to estimate what the difficulty of the task is as well, to at least having an upfront discussion as far as maybe rank sorting the difficulty of various tasks within the game so you can understand how much your team is signing up for. And then design points. So the concept here, this is something that Karthik from 1114 in Canada talks about all the time. The goal for your team should be to specialize in a strict subset of all of the available tasks that your team comes up with that are possible. Remember, the first part of this process is what is every single task that's possible in the game, from scoring in the trap, climbing on the chain with a partner, climbing on the chain with two partners, right? Those are just some lists of all the different things that you could do in a given game. The important thing to think about with the design point element is just because another team is doing it, that doesn't mean you need to do it. But even further than that, and this is probably, goes all the way back. Remember, golden rule number 1, I said, was going to come into play in all of this. The most important thing your team can do is to celebrate all of the things that you say we will not do this season. Okay? And this is very difficult. And I'm almost always the devil's advocate in the room on Kickoff about not doing things, because I hate doing more things with our robot. It sucks to have to do a lot of things with your robot, all right? And likely, if you try to do a lot of things with your robot's gonna suck, okay? It has to do less stuff, all right? It has to not score in the amp. It has to not score in the trap. It has to not buddy climb with another robot on the chain. Maybe it doesn't climb at all. Like, just start cutting stuff off, right? Because the more you cut off now, the less you're signing yourself up for, and the less that you've signed yourself up for, the more likely your robot will be simple, robust, and effective and reliable at the tasks that you do build. Yeah, cut scope. Your robot will suck if you don't cut scope. You have to cut scope. Agree to not do things and actually celebrate it, because what Kickoff does is it sets the entire trajectory for your season, and you will have a good, productive season if you do far less things than you are inclined to do. Okay? A lot of you in this room are probably going to be involved in the Kickoff discussion. A lot of you are going to be talking with your peers about what the robot should do. Okay? If you can be one of the proponents of doing less and saying we shouldn't do that, we should say no to that, and we should say no to that, you are doing more than anyone else on your team to be successful. All right? It's that simple. Do less things, you will be good. If you do more things, you will not be good. Okay?
So on the hows, so once you solidify what your robot will do, now it's time to discuss how your robot will accomplish those tasks. So the questions to be asking yourselves is, do you have experience with a design like this? Or is there a readily available example of a design that someone else did? Is it passive versus active? So is it just something, a good example would be in 2015, a lot of teams for their stackers just had pieces of polycarb that would snap and lock in onto the totes, versus a lot of other teams had an active wheel that would suck in and then raise separately and then suck in another one. And then how would you process that game piece? One thing that we even struggle with is everyone wants to focus on what kind of shooter we're gonna have, or a climber, or even the intake, but nobody thinks about how does it go from the intake into the robot where it can be stored, and then into the shooter or scoring mechanism. That's something that we struggled with a lot this year, especially in a game where I think my personal opinion is that First is going to be having a lot more either 2 game piece games or a game where you do 2 tasks with a game piece. I think that it's really important to think about how does the game piece not only just go from point A to point B, but now possibly to point C. And how can you make sure that all of this fits into your frame perimeter? And so it's really important to show your concepts, not just say, so I'm thinking of this arm, it kind of goes like this, picks it up, brings it in. It's really important to draw out your ideas because someone might be imagining a completely different concept with your word description, and drawing it out makes it a lot easier. It doesn't need to be this complicated CAD, it can just be a simple hand drawing, but it's really important to make sure that things are to scale so that someone else that's seeing it, that will be criticizing, critiquing, or accepting that design, has the same idea in their head that you had in yours.
Okay, so that's the first 3 days of season. All of our process around the first 3 days is what we just went over. Very dense first 3 days, but I talked about earlier, it sets the trajectory for the whole season. And then we go into the first couple of weeks of season. That takes us into a ton of prototyping, drive base, electronics layout in the drive base, kind of building up the foundation of the robot, fabricating and assembling the drivetrain, which goes along with wiring it. We begin writing code for mechanisms and systems we expect to have. So the software team starts getting going on the overall structure. Obviously, they don't have a robot yet to dial stuff in, but they're getting the basics done. And then assembling the alpha robot, which is going to take us to the next slide.
Yeah, so starting in 2022, we started building what we call an alpha bot, which is just a functional prototype, which is all of our different prototypes kind of built and mounted onto a single drive base. This robot is not legal. The intake prototype is just mounted on there. It does not retract into its frame perimeter. It violates the frame perimeter, or it violates the height restrictions. It's just a way for us to test our auto paths with a shooter or scoring mechanism and an intake. It allows us to start our driver practice early, and it allows us to understand your prototypes in reference to the field and reference to the game piece, the way that you're going to be playing it. There's been a lot of times where we've tested out our prototypes, and while it's in the prototype stage where it's isolated, it works great, but then once we put it together, we realize that the geometry of it doesn't fit with all of our other prototypes and what we're imagining for our robot, or that it just doesn't work in terms of realistically driving up and scoring. A really good example was our climber in 2022. We used the 125 chopstick method, and it didn't work at all once we put it on our beta bot, and we had to literally throw it into the garbage and start from scratch. And so having that alpha bot where we knew kind of the geometry of the hooks kind of made that transition a lot easier.
All right, and this takes us into the mid-season push. This is kind of going from week 2 through week 4. Like Austin talked about, we have that alpha robot usually done around day 10. And the next 2 weeks are all about building mechanisms. It's all the stuff that goes on top of the drivetrain is starting to take shape in the next couple of weeks. So hopefully by the end of week 3, going into week 4, most of the robot is built, and then it's all starting to come together into a final robot assembly that then the electrical team can take and wire up and get all the routing just right, and then the software team can start to do bring up on the various mechanisms to get the robot working.
So end of week 4, our robot should be more or less finished. That's when we go full testing mode. Our robot is on the field as much as possible. and we break our robot constantly, every driver practice, so then we know exactly where the intake tends to be failing, or we can't score in this method, and so it just allows us to spend as much time testing them and finding the failures in the shop, so then we can solve those problems and then solve them, or so that they're fixed when we compete. Every single time that, or every good team fails just as much as every other team, but they just did it in their shop rather than on the field, because they spent the time, they gave their drivers enough time to break the robot so that it didn't break a competition. And so that's Golden Rule 5, fail faster. Driver practice is really important. I try, my concept is that before your first competition, you should have at least 20 hours with the robot driving. It doesn't actually need to be 20 hours on the sticks, but 20 hours of your robot kind of operating and finding those issues and having your drivers get practice scoring with your robot will probably put you in the top 5 alone at your first competition. A good driver beats a good robot with a bad driver every time.
And back to the picture too. That's just an example of practice this year and all the ways that we beat up the robot. We got error in practice, and that became a Slack emote.
Yeah. I love
Anyway,
that.
all right, keep going. All right, getting to the competition season. Do not stop iterating on your robot. This is an example picture from this past season. This was our beta robot that we thought we were going to be competing with all year, and it turned out to be terrible. And so this is a picture of a few of our freshman team members responsible for disassembling basically the robot funeral. This robot lived from January
13th to the 31st.
January 13th to the 31st. So basically less than 3 weeks of life this robot had before it was taken apart, and we went in a totally different direction with our 2024 robot. So the point here is that the work doesn't stop. I think it's important to be careful and not bite off too much more than you can chew, but it's also important to recognize that everyone else is constantly improving. The game, if you look at any game, and Austin probably knows these numbers even more than I do, but if you look at any game in first that has any sort of linear scoring capability, the scores always improve over the course of the season. Week 1 scores are always lower than week 3 scores, which are always lower than week 6 scores, which are always lower than champ scores, except for a couple of district events. But for the most part. So the robots continually get better, and in this new era of first, where there's no bag, there's no stop build, there's none of that, you have to be improving over the course of the season if you want to stay competitive.
And part of that is learning what everyone else is doing. Watching other competitions is part of the key to our success, where we don't just have this magical way of knowing what the meta is of every game. Every year we see normally what 2056 is doing, and we then see what other teams are doing at their competitions, what's successful, what kind of autos are they running, because odds are someone else is smarter than you and figured out the answer. And so it's really important. We have a pancake breakfast every year to watch week 2 events, because we normally compete in week 1. And it's our first time. We have all of our students come. We watch the events. We have everyone read Chief Delphi. There's a bunch of new shows on Fun and RSN that talks about how teams did at competition, what a robot's doing, what's successful, what's not. Volunteering at events is a really good way to see robots up front and up close, to see and get an in-person look at what that robot is doing and what makes it capable of doing that. And it just allows you to look at everyone else and get general ideas of how you can tweak your robot, or tweak your strategy, or your auto, or your programming, just to make the most of the robot that you have.
Cool. So just to recap, Golden rule 1 and 2 for preseason prep was golden rule number 1. Keep it simple. And golden rule number 2. Steal from the best. Awesome. And then we go into drivetrain design, which Austin talked about. Rule number 3 is? Use a proven drivetrain, right? That's either likely going to be a kit bot if you've never used Swerve before and you don't get it working before kickoff, or if you have gotten Swerve working using an off-the-shelf Swerve solution. And then going into mechanism design, what's the big rule in mechanism design?
Rolling grabbers.
Rolling grabbers, awesome. And then good practices on electrical, pneumatics, and software. And then in build season, golden rule number 5 is? Fail faster, excellent. And then that failing goes all the way through the competition season, and keep failing, keep working, because the work never stops. You can always be better as a person, as a team. Your robot can always be better. There's always more work to be done.
Yep, and if you have any questions, you didn't put your info on the slide.
If you want my contact info, we can chat later, but
And
Austin's
that's mine. And then if you have any questions or feedback, we have a QR code for you to scan.
Please scan the QR code if you could right now and fill out the form. It's really important for our workshop organizing every year. We try to do these every year, but we always want to be improving. Just like with the robot, we want to be improving our workshop experience. So if you have any feedback you can provide, even if it's all positive feedback, that's another great data point for us to know that we're heading in the right direction with these. But if there's anything you can think of that you'd like to see improved, topics you'd like covered, other things like that, I think you can give a lot of that feedback through that short form. So other than that, thank you everyone, and we can take some questions.
Early in the presentation, you talked about preseason and the number of builds you did. How do you budget for that overall for your
A number of projects in the preseason?
Yeah.
How do we budget for it?
Do you just recycle old robots?
Yes, a ton of what we build with in the preseason is old recycled robots. The other thing that those preseason projects give us is sometimes we will use 1 or 2 new elements that we intend to take off of those practice robots and use in the build season. So it could be like, trying to think of a good example. Like this year, we're planning on, with one of our clone robots, using the new Swerve modules from West Coast Products that they just announced last week. But we want to try to use that on one of our practice robots in the fall before we use it in this coming competition season. So we expect to take those modules back off of the clone robot in about a month and get it ready to use in the competition season.
You're not worried about running out motors or anything like that?
No, I mean, for the most part, all of, like, the Kraken motor especially is a very reliable motor. If you treat them right, the Falcons were very reliable. They don't really sell them anymore. So yeah, all of those motor components now are pretty much just pull it off of one robot, put it on the next robot. Yeah, good question. Yes?
In terms of limiting your mobility,
Your scope?
freedom of movement.
Okay.
Range of motion. Oh, no, sorry.
Degrees of freedom.
Degrees of freedom,
Is
yeah.
there ever if you're running Swerve drive, is there ever a reason to use a turret if you're using Swerve?
So this is a controversial question.
I know 254 did that.
Yeah, and I'd say if you have the means in terms of you know how to build a turret and you have the software means to make the most out of it, then it can help you. That being said, if you're taking away from this presentation things and taking down notes, it probably will not serve you to build a turret with Swerve.
I think there's probably 5 teams in the world that would benefit from
Yeah.
a turret in any given season. And it's worth mentioning that in a year that everyone thought a turret was absolutely necessary, we had the most accurate, highest scoring robot in 2022 without a turret.
Yep.
In a sea of robots that had turrets. So it can, and that robot probably better than our last 2 years followed the
Keeping it
strategic
simple.
design
Yeah.
principle of keeping it simple, and it was our most competitive robot we've ever built. in
For sure.
22. Yeah.
Yeah.
Where will the slides, will you be able to see the slides on online?
Yes. Yeah. We post all of our all of our slide decks and the videos on our website under Fall Workshops. Yeah.
You open source your code on GitHub?
Yes, we do. Yeah, we have we have a link on our website that will bring you to our code, but we also have a Chief Delphi thread that will link you to that page if you can't find it. Yeah.
You mentioned earlier, or you mentioned in the slideshow that failing fast is a really good technique. Is there a specific way you can apply that in prototyping? Because at least for our team, I know it sometimes it takes a little way too much time out of our build season to spend a lot of time on prototyping. So are there faster ways to prototype or other key?
There are definitely faster ways to prototype. Focusing on making things quick and dirty, especially initially, making things out of wood is really important. I think a lot of teams focus on trying to make a prototype be the final design and making it kind of a quick throwaway proof of concept so that you can just quickly move on if it doesn't work and literally throw it away. Or something that you can then, if it's simple wood, you can just mount it to something and see if it actually runs. That we were lucky enough to add a laser cutter 3 seasons ago, which that helped a lot with our speeding up our prototypes because we just would make a quick plate and cut it out of wood or polycarb. But not being afraid to drop a prototype, I think, is the way to succeed in terms of that.
The only thing I want to add is prototyping is another thing that your team can practice in the off season.
Oh, absolutely, yeah.
And we do off-season prototyping. Like the clone robots are not really a prototyping opportunity. We don't do any prototyping. We just build based off the CAD that someone else published. But you can also run prototyping challenges where you divide your team into a couple of groups and you give them a bunch of hand drills and plywood and duct tapes and a couple of wheels and say, try to do this task, right? And then you give everyone an opportunity to really, like in a couple of days, sprint and try to find some functional solution with the given tools and stuff you have available. And they can take those lessons into the build season.
Yeah.
During kickoff, how do you guys measure the difficulty of the task? Because for our team in particular, this year we struggled a little bit separating the difficulty of the task with like what mechanisms you can use to accomplish this task.
I think when we talk about the difficulty of a task, I think that we normally talk about the difficulty, at least during the what's discussion, we talk about the difficulty in terms of accomplishing it in a match is a lot of what we talk about. And the things that are normally harder to accomplish within a match are things that are harder to actually design. So a really good example would be climbing with another robot, so like a buddy climb. Having to rely on another robot is an extra level of complexity, but that's within the match. But then that also applies on you have to build a robot that is then compatible to work with another robot. And so I think that there's kind of a direct relationship there. And I think that for us, we spend a lot of time, we know FRC history, so we kind of know the general gist of how difficult something is and what the kind of hard climbers are versus maybe an easy climber. So knowing FRC history will help a lot there. Mike probably.
Yeah, I think a couple of variables you can think about too. I think that's all right because you have to rely on your experience a lot. And that's studying past games is one of the best ways to give you an idea of what's viable and what's not in the future year. But there's also a couple other things you can think about. Austin mentioned coordination. That's one thing. If it takes a lot of coordination between robots, it's probably very difficult to pull off. Another one is alignment. So if it requires very precise alignment to pull off, it's probably going to be very difficult. The last thing is physics. So simple physics problems are also important here. So like the physics of shooting a cargo into the goal in 22 was a lot easier when you were 3 feet away, and it got a lot harder when you were 30 feet away, right? Or the physics of pulling up on the first level of the bar in 22 was a lot different than the physics of getting from bar 1 to 2 to 3 to 4 within while following the rules of the game that year. So physics is going to be another one that you need to respect when you're talking about level of difficulty of some of these tasks. Yep.
Yeah. So, I guess we normally have 2 to 3 versions of our prototypes. We have the quick, like, first couple days of prototyping version. And then after we see, yes, this will work, we make another version, normally just out of like polycarb, and a simple plate. Normally 1, maybe 2 plates to make it work, and as minimal rollers as possible. And then that can be mounted onto the AlphaBot. Normally it's not our first prototypes are the things that are mounted, but that's also because our dirty prototypes are the ones that are like, our shooter this year was held up by like 2x4s stacked on top of each other. And that was kind of just holding that while we held the shooter in place to see if it was working. And then we made kind of a more fixed version of it, and then put that on the AlphaBot. And then if there's some sort of big problem with that, then we might swap something out from there. But normally after that, we get the purpose of the AlphaBot is to get a general idea of how the mechanism will work or what the failings are of it, so that then you can build your first real version. The AlphaBot shouldn't really be used for 4 weeks, if that makes sense.
Yeah. So it's usually very dirty. And I'd say, like, we had some wood gussets on the robot this year.
Yep.
That just completely got demolished, and we eventually swapped out for a metal plate. But that was after quite a little while. Like, we dealt with the shooter going like this a lot on the Alpha robot.
Right.
So it didn't really make a lot of goals, but it didn't really have to. We were like, that would have gone in, pull
Had
off,
it not,
had the shooter not been falling off. Right, but it still had a working intake and an indexer, and so it would go back and forth and do the cycles, so we still learned a lot, right? But yeah, the Alpha heavily leans on the dirty side of things. Yeah, let's do one more question, and then we'll break, and then after we break, if people have follow-up questions, we'll be right up here to answer them. So yeah, what's your question?
How during the prototyping phase, especially the first 3 days of this brainstorming, how do you end that? How do you come to an agreement on an idea? Because that was our problem this year, is that we could not agree on an idea for like 2 weeks.
Yeah, if we get into the mechanisms of that process, you need to have a lead that is facilitating the discussion and working to build consensus and ensuring that consensus is built eventually. So what Austin knows, the way that we do this, and a lot of our citrus kids know this because they all go through the process, we have small group discussions, then large group discussions. We have a lot of ideas written on the board. Some of them are crazy and we can eliminate them right off the bat. Some of them are sure things, like we're definitely going to do that, and we circle it, we lock it in. And then other stuff is on the bubble. And so we spend a lot of time kind of circling around, and it's kind of going down the drain until we all land in the same spot. And some of those last discussions, we try to get to the really contentious stuff by the end of Saturday so that everyone has a day to sleep on it, and then we can come back with fresh ideas on Sunday and begin the discussion on like the 3 or 4 remaining contentious topics, and then continue to work our way through. But you need to have someone who's leading that discussion, who's always the fallback person as the discussions start, because they will devolve over time. They'll go on tangents. They'll get too personal. There's all these sort of things that happen within those broad team dynamics, and you need someone at the helm to lead all that. That's usually my role, and I'm making sure that the consensus is actually achieved by the end of that second day. So it's not easy. It's a very difficult process, especially because we have 120 people in the room when we do that. So
yeah. So to the point of like specifically deciding on what prototype to go with, because normally if you have a shooter, you probably have at least 2 different kinds of shooter prototypes. Which one are you going to go with? I was pulling it up. I have a picture from Spectrum's design presentation that they did at the Mentor Conference. Things we don't do. Vote. Absolutely not. It's not really a democracy on a team, and it then leads to people that don't have the specific knowledge and experience to say what they think is the best design. They end up having an equal vote an equal say in terms of someone that has a decade worth of experience as a mentor or one of your lead design students. So normally it's the people that are heavily involved with the design that have been testing them, and you have a weighted decision matrix, so something that can thoroughly go through the pros and cons of each one and say which one has maybe the higher capability versus which one's more reliable, and then it's the trade-offs between those points rather than just which one do you like better.
Okay, we'll break right there. Thank you, everybody. If you have other follow-up questions, we'll be right here, and we can chat about it with you. Happy to do so. But have a great rest of your day at CCC. Thanks, everyone.